In today's lecture, we will learn how to graph functions using calculus. So the first principle we need is how to tell when a function is increasing or decreasing. So here we have an increasing function, and in this picture we have a decreasing function. Now, if you take a tangent line at every point of this graph, you'll see that the tangent line will have a positive or non-negative slope. The tangent lines go in the same direction as the graph. So the conclusion is that the derivative is greater than 0 when the function is increasing. On the other hand, this is a decreasing function, and if you look at the tangent lines, you can see that generally they're decreasing and the slope of the tangent lines are negative. So the conclusion here is that f prime is less than 0. So if a function increases, its derivative is positive. If a function decreases, its derivative is negative. The graph shown here is the original function f of x, and f prime is not shown. Okay, so that's our first principle, and let's use that to figure out when a particular function is increasing and decreasing. So for our first example, let's look at the function f of x is equal to 3x to the fourth minus 4x cubed minus 12x squared plus 5. And the question is to figure out when is f increasing and decreasing. Alright, so if you want to pause the video for a minute, you can see if you can solve this on your own. Okay, so the first step is to compute the derivative function, and we get 12x cubed minus 12x squared minus 24x. We need to find the critical points. Polynomials are defined everywhere, so the derivative exists everywhere. So the only kind of critical point we can find, critical number per se, is when you set the derivative equal to 0. So let's solve for x. Factor out a 12x, and what we're left with is x squared minus x minus 2 equals 0. And this further factors to 12x times x minus 2 times x plus 1. So the critical numbers are x equals -1, 0, and 2. Okay, so we have our critical numbers. We need to figure out when the derivative is positive or negative. knowing when it's 0 is very helpful, because we can now make a little number line here for the first derivative. So f prime. So on this number line, let's put the critical numbers. -1, 0, 2. Okay. The derivative, and this is the derivative, the derivative only changes sign at the critical numbers. So to find the number line for the derivative, we simply plug in a point in each range, and if it's positive, it must be positive everywhere, because it can only turn to be 0 at the critical numbers. So let's see. Let's try -10. A negative times a negative times a negative. 3 negatives multiply to give you a negative number. So the conclusion is you're negative everywhere to the left of -1. Let's try a number between -1 and 0. How about a half? Negative a half, sorry. Negative a half, so 12 times negative a half would be -6. That's negative. Negative a half minus 2 is negative. Negative a half plus 1 is positive. Negative, negative, positive. That multiplies to a positive. So put plus signs here. Let's try the number 1. That's between 0 and 2. Positive, negative, positive. That gives you negative. Doesn't always change sign this nicely, by the way, but in this case it does, because there's no repeated roots. And try a number bigger than 2, like 100. Positive, positive, positive. 3 positives clearly multiply to be positive. Okay, so now we know where the derivative changes sign and where it's negative and positive. So the conclusion is the function f is decreasing, then it increases, then it decreases, then it increases. Okay, so we've solved this problem, and we're getting closer to actually graphing this function, but we're not there yet because we need what's called the second derivative. So the second derivative is also useful, and it gives you different information than the first derivative does. So let's look at some pictures. All right, so here's the graph of f of x. Here are 4 graphs. And you can think of these 2 graphs as sort of going together as being part of this graph. Next, we have a graph like this, and a graph like this. And you can think of the 2 graphs fitting together and giving you parts of this graph. Okay. So the top graphs are called concave up. So concave up. Bottom graphs are called concave down. Now, what makes you concave up or concave down? Well, look at the derivative. the derivative is the slope of the tangent line. See how the line is getting steeper and steeper? The derivative is increasing. So when you're concave up, f prime increases. If you were to walk up this mountain, each step would be harder than the step before. In this case, the derivative is also increasing. It's just going from more negative to less negative. But that's technically increasing on the number line, going from left to right. So in both cases, f prime increases. And if you're any part of this graph, you're concave up. Here, the derivative decreases. See, look at the tangent lines. Each tangent line is getting less steep. It's easier to take step by step. Each step you take up here is easier than the step before. The curve is flattening out. So the derivative is decreasing. So here, f prime decreases. Here, the derivative is becoming more and more negative. That's decreasing. So any part of this graph is considered concave down. So if the first derivative increases, that means the derivative of the derivative is positive, right? So that means f prime, the derivative of the derivative, which is f double prime, is greater than 0. So when the second derivative is positive, the function increases. And in this case, when the second derivative is negative, sorry, I think I said that wrong. When the second derivative is positive, the function is concave up. When the second derivative is negative, the function is concave down. So along any part of this graph, the second derivative will be positive. Along any part of this graph, the second derivative would be negative. Alright, so let's try an example. We'll go back to the example we had before, and we'll now figure out all sorts of interesting things about the graph. So we know about concavity. We know about when the function increases and decreases. There are a few other special points we'll see as we go through the example. So let's go back to our example. So we'll go back to f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. Remember, we found the derivative as 12x times x plus 1 times x minus 2. And we said f increases from -1 to 0, and from 2 to infinity, and decreases from minus infinity to minus 1, and between 0 and 2. So let's look at the second derivative now. So you can't take the second derivative from here. You're better off going back to the unfactored form. So let's rewrite this first derivative. 12x cubed minus 12x squared minus 24x. So the second derivative is equal to 36x squared minus 24x minus 24. Let's factor out a 12 from here. And we get 3x squared minus 2x minus 2. We're looking for when the second derivative changes sign. So it changes sign when the second derivative is 0. So we find the zeros of the second derivative, and that will allow us to find when the second derivative changes sign. So solving for x, we'd use the quadratic formula. So x is equal to negative b, 2 plus or minus the square root, b squared, so that's 4 minus 4ac minus 4 times 3 times minus 2. All divided by 2 times a, that's a 6. So what do we get? 12, 24, 28. So we get 2 plus or minus the square root of 28 divided by 6. So this problem is a little bit more complicated numerically. So I'm going to give a simpler example in a moment, but to continue here maybe with a calculator, you would once again repeat the process we did before when we found when the derivative is positive and negative, but for the second derivative. So you repeat the exact same process again with a number line with these two numbers on the number line. But let me start over with a simpler problem so it won't get too complicated, numerically, and we could see the new calculus ideas a little more clearly. But in principle, that's how that would work. So before we get to that, let me give you a few more concepts. So a local max is something that looks like this. So for example, here's a local max. Notice for the local max, the derivative is positive here, and then the derivative is negative. So positive, negative. The derivative changes sign at a local max. And that's how you can find the local max. So if f prime goes from plus to minus, changes from positive to negative, then you obtain a local max. On the other hand, something like this would be a local min. And if you look at the derivative, the slope of the tangent line, it's negative. We'll always go from left to right. The notation is always to go from left to right. So we're negative, but then we're positive. So if f prime changes from negative to positive, that's called a local minimum. So that's how we can figure out what the graph may look like. And finally, a point of inflection would be where the concavity changes from up to down or down to up. So the picture for a point of inflection is something like this. So see right here, here you're concave up. So you're concave up. Here you're concave down. This point here is called an inflection point. Same thing here. And it looks like there's one here. So here we're concave up, here we're concave down. But look what happens. Over here to the left, the second derivative is greater than 0. To the right, concave down, the second derivative is less than 0. So these tests, looking at the sign changes of the first and second derivative, would allow us to figure out inflection points in the second derivative case and local max and mins in the first derivative case. Alright, so let's try a full example where we will sketch the graph using calculus. Alright, so f of x is equal to x to the fourth minus 4x cubed. The first derivative is equal to 4x cubed minus 12x squared, which factors to be 4x squared times x minus 3. Alright, the second derivative is equal to 12x squared minus 24x, which you can factor as 12x times x minus 2. Alright, so let's compute the number line for f prime. So the roots are clearly 0, the critical numbers are clearly 0 and 3, setting it equal to 0. So we have 0, 3. At both places, the first derivative is 0. Try a negative number like negative 3. Negative 3 squared is positive. Negative 3 minus 3 is negative. Positive times a negative is negative. Let's try the number 1. Positive, negative, still negative. 4, positive, positive, so we're positive. Okay, so far we can figure out when the graph is increasing and when it's decreasing. So over here it's decreasing, decreasing, increasing. See how it decreases and then increases? That has to be a local min. Decreases, decreases, but flattens out. It has to look like this. See, it decreases and decreases, and right here it has the horizontal tangent line. Okay, so we have a local min, so 3 is a local min. Let's repeat the process for the second derivative to figure out the sign changes. So f double prime changes sign at 0 and 2. Alright, -3, -5, plug in -3. A negative times a negative is a positive. Plug in 1. Positive times a negative is negative. Plug in 3, positive, positive, multiply to be positives. Okay, so what we know is we're concave up here, we're concave down between 0 and 2, and we're concave up. So we have two inflection points, inflection point and inflection point. Alright, now we can put it all together and try to graph. So let's see if we can come up with the graph. So you might want to pause the video for a few minutes and see if you can graph the function from this information. Let's see what we have. So we're going to be coming down, decreasing, and then we're going to get to the local minimum and then increase. When we come down, we're going to be concave up. Then we're going to switch to becoming concave down at 0, and then we'll become concave up forever. And don't forget about the local minimum. Alright, so without drawing an x and y coordinate axes yet, first try to come up with the sketch. So let's see. We're coming down, we're decreasing, we get to 0, we flatten out, we decrease and increase again. So this point right here must be 0, 0. If you plug in 0, the y value is 0. Okay. Next, we change concavity right here. So see here we're concave up, here we're concave down. It's not a perfect picture, of course, but you can see the point. At 2, we change concavity again. So here we're concave down, here we're concave up. So right over here, you have your point of inflection. I'll just put an I over there. So let's draw the coordinate axes. So right here, we're at 2, and right here we're at 3. That's our local minimum, but if you look at it, it's actually an absolute min. It's the lowest point in the entire graph, because we're decreasing and then we increase. There's only one minimum, and this has to be the global or absolute minimum. This must be the lowest point anywhere, because the graph decreases and then it increases. So it never gets lower than that point. And this is the correct graph. I encourage you to try to do this on your own. Start here, and maybe try to redo the problem without looking at the video. Now, let's do one more example, maybe one that's a little bit more complicated. At least we'll get it started. So let's start with the sine function. Here's the problem. Graph y equals sine of x on the interval from 0 to 2 pi, and identify local max and min and inflection points and intervals of concavity. Okay, so we start with f of x equals the sine of x. F prime of x is the cosine of x. And f double prime of x is negative sine of x. First, let's find the critical numbers. So we set the cosine equal to 0. Well, the cosine is equal to 0 at x equals pi over 2, right? 90 degrees. And 3 pi over 2. Right? If you don't remember, I know it seems like we're cheating using the graph to answer these questions, but you just need to really know where the graph crosses the axes. So here's the graph of the cosine, and either using the unit circle or memorizing the graph, 90 degrees, 270 degrees, 3 pi over 2. Okay, so understanding the graph of the derivative, we can figure out the number line for f prime. So let me just draw it right here for f prime. So we have 0, 2 pi,